today we are going to talk more about our carboxylic acids and derivatives. We're going to start today by talking about acid halides and anhydrides. Those are going to be our most reactive derivatives. And we're going to see they're the ones that we can do the most with because they're the most reactive. So just recall, if we want to make an acid halide, we just need to put it with some thionyl chloride, and we will get our acid chloride and I think some sulfur dioxide and HCl, but side products, who cares? Main point here is that we halogenate our acid halide, or acid, that we form the acid halide. So that's the big part. All right, so this is the most useful one. You want a mechanism? Oh, you're right. So last time, did I use this tablet? Let's find out. I did. Okay. So this mechanism that I showed y'all here at the end, this one's a longer version. We can do it. Oh my god. We did so much naming last time. All right. With this one, if we actually start with the OH as our nucleophile, we can do this mechanism a little bit more quickly. And so I'm going to show it to you that way too, just so we have it so we don't have to spend too much time on it. Thank you, Eric, for the reminder. Okay. All right. So let's just do this real quick. So we're going to, it's the same mechanism, but we're going to be starting with the OH, so it's going to save us a couple of protonation steps that we would otherwise have to deal with.
This is from how do we make carboxylic
acid? So this is how we're going to make the acid chloride from the carboxylic acid.
Oh.
Okay. So it's this reaction right here. So last time I had started off with this guy as our nucleophile. It's actually going to be a little bit more efficient for us if we start with this guy instead. And we'll see why. So we're going to go ahead and attack. Oh, I'm using this. Okay. Open that up, just like before. If we do that, we're going to go ahead and now have a connection between our our acid oxygen and the thionyl chloride. I'm going to put that thionyl chloride just on the side here, so I've just tilted it a little bit. This is got a negative charge. That's going to close down, kick out a chlorine. So if we do that, everything else stays the same. We'll let our positive OH there. So now we're going to go ahead and deprotonate this. So we're going to have some base, could be chloride, could be whatever. Let's just use chloride. Going to come in, grab that proton. Which makes the neutral one. So see, it's exactly the same as the last one, just a few fewer steps. All right, remember that this little bit here is a great leaving group. So what's going to happen is we're going to have one of our chlorides come in. Going to attack our oxygen, or carbonyl rather, not the oxygen. Pop that open. All of these reactions, they to the carbonyl, they end up popping it open. You make that tetrahedral intermediate, and then you close back down again. So it's exactly the same thing here. All right. And then finally we close this down and kick out our leaving group, which can then go do other things. What's actually going to happen here is we end up actually not only kicking out the sulfur bit, but we actually end up producing another chloride ion, which is where we have extra chlorides hanging around, one to act as a base, one to act as a nucleophile, and then we will end up with our acid halide as well. So we have our acid chloride, we make our SO2, and then we make another HCl. All right, overall, this is the overall reaction. So a little bit faster if we start with the OH1. Can start with the other one. It's just going to be like 3 more steps of protonation, deprotonation. So let me go vertically here real quick. So first step, attack the thionyl chloride, opens that up. It then closes back down, kicks out a chloride. We do a deprotonation. Next, we have a chloride come in and attack the carbonyl, pops that open, makes the tetrahedral intermediate, closes back down, kicks out the sulfur containing leaving group, which then forms SO2. And this is going to be the entropic driving force behind this reaction. So we produce a gas that's going to help drive this reaction forward by Le Chatelier's principle. All right, so that's the more abbreviated mechanism for this transformation. And you know what? Actually, I want to do one more thing, because this was a pretty common mistake on the exam, so I do want to address that as well really quickly. All right, so I'm going to go ahead and horizontalize this, if that's okay. And I'll leave this up here. Something like this thing, or I think because we had this on, I'm going to make it in a group. We had this on our exam, or there was something that used this on the exam, right? With peroxy acids, the only thing that they do is they add an oxygen. So it doesn't matter which of these peroxy acids you use. All that happens is you end up putting an oxygen into your molecule. You end up making an ester out of it. So, and if you have an aldehyde, remember that we talked about like which groups are easiest to migrate when you're putting in this. If you put, no matter what your peroxy acid is, all you do is end up oxidizing this. The R part doesn't matter. It doesn't figure into the final product. The only thing that matters is the oxygen. So you end up inserting an oxygen to your best kind of place. Remember that like which side gets the oxygen? H is best, then tertiary, then I will say phenyl, then secondary. These are about the same actually. And then primary, carbons, right? So the first priority for putting in that oxygen is next to the hydrogen, so you make it a carboxylic acid. Otherwise, you're going to put it with your more substituted carbon. And the R group does not matter. The only thing that gets added is one oxygen atom. And it's going to get added according to this priority. So a lot of y'all tried to kind of cheese that by using it as kind of, aha, now I can throw in the rest of this molecule. No, for that you gotta, for this one you have to do a Grignard and then an oxidation, and then you can do the MCPBA or whatever peroxy acid. So that was just one thing from last time that I had noticed, that a good proportion of you misinterpreted. Okay, so hopefully that makes it a little bit more clear. So all you add is an oxygen atom. The R group does not matter, and it does not come into play with this sort of reaction. Okay, so I will write that out in purple. So I'll make that more clear. Okay? Cool. Okay, so that's old stuff. So now we can actually do what I wanted to talk about today, which was the acid chlorides. So let's go ahead and take a look at some of these things. So acid chlorides, their main reaction will be to be combined with some sort of nucleophile. And how this works, mechanism-wise, they're all completely identical, except for two. Two of them, they just happen twice. So it's always at least a two-step process. So first step is we pop open our carbonyl. And then it just depends what's going to happen here. We can either go backwards or we can go forwards. So with this, we can either kick back out our nucleophile, depending on how good a nucleophile it is, or we can kick out the chloride. Generally speaking, that's what's more likely to happen because chloride is a good leaving group. So we're going to end up substituting at our carbonyl whatever that nucleophile happened to be. And we're going to see for most things, it's a pretty, you don't need a very good nucleophile because chloride is a pretty good leaving group. So we're going to see a couple of things will happen when we combine them with acid chlorides, and we have a lot. So let's go ahead and take a look at some of them. So the R group, again, doesn't matter. I'm going to copy this because we're going to be using it a lot. If you put this thing with water, you're going to get the acid out again. Typically, by the way, when we are forming OHs or oxygen-containing groups, we also put in some pyridine. The reason for that, when we use the pyridine to kind of sequester the chloride, because as a result of this reaction, we're going to get HCl. And while it's not necessarily that bad to have it with the carboxylic acid, we're going to see that some of these other functional groups can be sensitive to acid and will hydrolyze or do other things in the presence of acid. So we use pyridine to kind of gobble that up. So if we use pyridine, it forms pyridinium chloride, which is a nice precipitate, which will gobble up our HCl, and we can just filter it out. And it kind of separates that. Actually, it's not gonna... This thing, the pyridinium chloride, once we put those two together, this is a salt, right? It's a precipitate, so it gets it out of the reaction, so we don't have this bothering us anymore. So it's a way of getting rid of the HCl. So that's a byproduct. So with hydrolysis like this, it's not terribly important because there's not really any way for us to get back to the starting material. This is not really an equilibrium reaction. But we're going to see if we try to make an ester and we didn't get rid of the HCl, we would end up hydrolyzing it to the acid again. So let's take a look at that. So with that, we just need to, if we wanted to put on an ester, we would need an alcohol here. So I don't know, how about ethanol? You would also want your pyridine here. And again, this one, it's pretty specific that you want pyridine. You don't really want other bases. It's because pyridine forms this very nice precipitate that says triethyl ammonium chloride may not. So doing this, you'll end up substituting in. You'll make your ester. And you'll get rid of your HCl because, again, HCl can hydrolyze your ester, so you don't want that. So pyridine here to, again, get the HCl out of the picture. So just some alcohol plus your acid chloride turns it into an ester. All right, so we want to generally put in pyridine for doing these two, and the rest, not so much. All right, what other nucleophiles do we have? How about amines? If we put ammonia, at least 2 equivalents, we will make an amide. And this amine can be substituted as well, so it doesn't have to be ammonia. We could put in a primary amine. To fix this, NH2R, there we go. And again, you need at least 2 equivalents here, because one of them is going to just have to react to HCl. So while the purpose is not to draw the HCl out, it's just because HCl is just going to gobble up your reactant. So it's not going to end up hydrolyzing your product or anything, but in this case, you need it just to prevent the, because your other product will just be NH4Cl. You just need something to get the HCl so it doesn't then react with your amine, because amines are bases. So if you use a primary amine, you'll get a secondary amide. And you can use a secondary amine as well. Again, you'll need at least 2 equivalents here. You can just say excess, that's fine. And you'll end up getting a tertiary amide. So acid chloride plus an amine, at least 2 equivalents. You're going to end up getting the amides corresponding to those. So, fun stuff. What else can we do with these? How about some, let's do some carbon nucleophiles. With a group, yeah, go ahead. These are all amides, yes. So, because all of these were amines that we're putting with. So acid chloride plus an amine, whatever substitution that amine happens to have, you'll get your amides out. All right, tertiary amines don't react this way. So ammonia, primary and secondary amines only, because tertiary amines are not nucleophilic. They're only basic for most reactions. Okay, so if we go ahead and take a Grignard reagent with this, we're going to see that we're going to need, first off, 2 equivalents, and then we're going to need some water at the end. Because what happens here is, just like before, we're going to have nucleophilic attack, kick out our chlorine. What actually happens is, oops. Actually, I'll do this in 2 steps. I'll do this in 2 steps, even though we can't really stop this reaction from happening, at least this way. We can't stop this because a ketone can also be attacked by a Grignard reagent, right? We've seen that. So you're going to first technically make your ketone, and then you're going to go ahead and continue. You're going to make the alkoxide, and then a water wash will finish that off. You can use acid as well if you like, but water is generally good enough to get this to happen. So you need to have 2 equivalents, because if you only put 1 equivalent in, you're not only going to get the ketone, you're going to get a mixture of acid chloride, of ketone, and of this tertiary alcohol. So with Grignard reagents, you're going to need 2 equivalents, and you understand that you're going to get the tertiary alcohol at the end. We do not stop here. We're going to see we have a different nucleophile that we're going to learn. If we do want the ketone, we're going to see what we'll use for that. All right, so if you take an acid halide and a Grignard reagent, you will need 2 equivalents, and then you'll need a water wash. and you'll end up with a tertiary alcohol. Unless you're starting with formal chloride, I guess, but we'll not worry about that. Okay, so you'll end up putting 2 of those alkyl groups onto your carbonyl carbon. Alrighty, but what if we want the ketone? Here comes in a new reagent for us. We are now going to, instead of having Migbur, we're going to have Coolies. These are often written R2CuLi. These are dialkyl lithium cuprates. Or more commonly, Gilman reagents. And we're going to see that with these are a bit more selective. These will not react with ketones. And so this will be the important part. These do not react with ketones. So they'll only react with acid chlorides or anhydrides. And so we're going to see here that if we wanted the alcohol, we can use Grignard. If we want the ketone, though, we're going to want to use a Gilman reagent instead. And so, for example, let's take this. Let's say we're going to take this is what it would look like. For example, I have diethyl lithium cuprate. Typically, these are symmetrical, by the way. What you end up getting is the ketone of these. So you'll end up attacking your nucleophile, but these are not strong enough nucleophiles to attack a ketone. So they can only attack the acid halide or anhydride. Remember, if we tried this with a Grignard, do the same thing with a Grignard, we're going to end up getting, let's try that again. We end up putting 2 of them on. Right, so Grignard will not work for making a ketone from an acid chloride. Not necessarily to say alcohols are sad, but we know they react with ketones, right? This is, I think you did your Grignard synthesis of triphenylmethanol in lab, maybe. So you've reacted Grignards with ketones. You know they react together. So, but with Gilman reagents, they don't. So with Gilman, you can stop at the ketone if that's your interest. So acid chloride and a Gilman reagent gives you the ketone. Acid chloride and the corresponding Grignard reagent gives you an alcohol. So remember, you do need a water wash at the end there, but it's our reaction. All right, so just in generic form, end up putting your R group on. All right, so the Coolies now, not the Migburs. All right, so that'll get us to making ketones out of our acid chlorides. All right, how about, let's see, reduction. So those were carbon nucleophiles. Let's look at hydrogen nucleophiles now. If you go ahead and use lithium aluminum hydride, strong reducing agent, you are going to get the alcohol out. It'll be a primary alcohol. So using a reducing agent on a carbonyl compound like this will generally reduce it all the way down to the alcohol. So lithium aluminum hydride will do this for us. First, technically, it reduces it to the aldehyde, and then it takes the aldehyde and reduces it to the alcohol. So we have a similar situation here. We technically stop at an aldehyde, but then we go ahead and react that with lithium aluminum hydride. So we're going to see we have some reducing agents that will only reduce to the aldehyde and stop there. Just like our Gilman reagents stop at the ketone, we're going to see we have some of these reducing agents that will do the same thing. All right, so if we use a much bulkier one, this lithium tri-T-butoxy, or even just butyl, you don't even need the T-butyl on there, some sort of bulky thing will help out here. And then we do the actually, we probably don't need no, we are going to need a water wash at the end, because we need that to come down. With this, we are going to end up just getting the aldehyde out. So these reagents are much milder. And it can't reduce the ketone or aldehyde. So we're going to be putting on some alkoxy groups onto our lithium, onto our aluminum, and those are going to end up kind of deadening the nucleophilic capability of the hydride that's on there. And so we're going to end up not reducing our aldehyde further. So if we want to reduce it all the way, let's throw in lithium aluminum hydride, you're good to go. If you want it to stop at the aldehyde, you want to put some sort of lithium alcohol or aluminum trialkoxy. It really is just OR3. Something like that. With the H will get you to the aldehyde. But the T-butoxy is a pretty common one. So that's how we can kind of curb the reactivity a little bit. So how many functional group transformations was that? Let's see, we did, here, let's go all the way up to here, I'll stop for a sec, and then we'll go ahead and look at the top so we can see all the fun stuff that we've done so far. Alrighty. Let's take a look, shall we? All right. Look at all the transformations we've done. Sorry, started here. Okay. Water gets you to the acid, and alcohol takes you to the ester, both of those using pyridine to sequester your HCl. We can put amines in of various types, and we get various amides out. We have carbon nucleophiles. We can put Grignards in here. If we put a Grignard, we end up putting 2 of them on, and we will fully reduce down to the alcohol. With the Gilman reagents, though, we'll end up with a ketone instead. So Grignards add twice, Gilmans add only once. And then with hydrogen nucleophiles, we can have the harsher reagent, the lithium aluminum hydride, gets us all the way down to the primary alcohol. And if we use some modified lithium aluminum trialkoxy hydride, then we are going to only stop at our aldehyde, which then we can do aldehyde things with. So from this thing alone, look at how many various things we can do with it. It's pretty remarkable. These are very, very useful functional groups. So we can do all sorts of fun reactions there. Yes, depending on which reducing agent you use. So harsher ones go all the way to alcohol, milder ones get you to the aldehyde. All right, and so, sorry, go ahead. Oh, T-butyl, yeah. Yeah. I get it. Yep, there's a lot of letters in that. This one, by the way, technically you'll want 2 equivalents plus for your lithium aluminum hydride, because since you are putting on 2 hydrides on there, because you technically have that intermediate, that's the aldehyde, that's hard to isolate. If you only put 1 equivalent, again, you're going to get a mess of products. So by putting 2 equivalents, you're going to make sure that everything goes all the way to the alcohol. All right, with this fancy one, though, you only need 1 equivalent because you're stopping at the aldehyde. Alrighty. And the water wash is just to get rid of the aluminum bits because they go complex and make weird things happen. All right, cool. Other questions on the acid chlorides? Mechanism for these is all identical, right? So nucleophile attacks, opens it up, closes down, kicks out chloride, and you're done. All right, so fun stuff. Fun bit next is that anhydrides do, well, anhydrides, oh, that's how you spell it. Okay, anhydrides do exactly the same things as all of these. All the same reagents, all the same products. The only difference, your starting material is a little bit different. It's exactly the same process. The only thing is our leaving group is not a chloride, but it is now, it's going to be a carboxy is our leaving group instead. So, just like before, things close down, we end up kicking out our, technically, since this is a carboxylate, we would need, it would have whatever our nucleophile's counterion is with it, so if it's sodium or whatever, it'll be there. He'll just go. Doggo on the move. Okay, well, she's off doing something. So, same thing. Everything happens exactly the same way. Throw a Grignard on it, you need it to react twice. Throw the lithium, aluminum, tri-T-butoxy hydride, get the aldehyde out. Throw a primary amine, you get a secondary amide. So, hooray, you get all the same exact reactions to happen. The only thing that is different is your leaving group. The only thing that's different is your leaving group. So everything happens exactly the same way, you just get a different leaving group out. Because it's a different leaving group, you don't need pyridine when you're doing hydrolysis or making an ester. You do not need pyridine in there because there's no HCl. With no HCl, there's no need to go ahead and scoop it up. So you're more than welcome to use anhydrides anytime you would use an acid chloride instead. So they work just exactly the same. All right, your leaving group is just different. Technically, you could make the argument that the atom economy is a little bit less since you're losing half your molecule as a leaving group. But then you also consider, well, I don't have to put in pyridine and putting in pyridine is also pretty wasteful, right? So it's like, I think there's arguments on both sides. So you can use either one in your synthetic routes. You can talk for a moment how to make anhydrides. If you heat the crap out of these acids, you will get an anhydride out. Symmetrical one. The symmetric anhydride. So you end up with both things on either sides. The temperatures required for this are pretty high, like hundreds and hundreds of degrees. So typically it's not the best way to do it. There are ways you can add activating agents like DMAP and things, and if you really want, or you can just do this. Go ahead, put your thionyl chloride in, make your acid chloride, and if you go ahead and use a carboxylate, you can go ahead and substitute that in. You can even say R prime because this one doesn't have to be symmetric. You will end up getting your anhydride out. Now this is say prime there, just to show that they could be different R groups. So if you want to take a carboxylic acid, make it into the acid chloride, and then you can convert it, but what's the point, right? Like, if you already have the acid halide, like, why bother? So it seems like it's extra work, right? So if you have an anhydride to start, you're good to go. However, if you're trying to make it, it's probably easier to just make the acid chloride and go from there. So, because then it's just extra steps, right? So, but they do exactly the same things. So, just replace RCOOCl with an anhydride, and you make exactly the same products as you would with the acid chloride. All right, so let's do some examples. Let's go ahead and do this one. Let's see, what are we going to get out here? Let's analyze, see what functional groups we're working with. We have an anhydride on the left, and we have an alcohol on the right. So what are we going to end up making here? Well, this is actually a little bit more complicated than I wanted to start, so I'm going to make this a symmetrical anhydride. What's going to happen here? Doesn't matter which one we attack. Oh my gosh, what did I choose? A complicated molecule. Okay, there we go. So we will have attacked our carbonyl, closes back down, and that carbonyl then makes the choice. As this closes down, what's the best leaving group? Are we going to have a phenyl group leave? No, we don't have carbons as leaving groups. Are we going to have this alkoxide leave? Technically, it's a protonated one, but we'll deal with that later. Or are we going to have this resonance stabilized carboxylate leave? Aha, and that's the answer, right? So we're going to end up kicking out our carboxylate, giving us the corresponding ester. Wow, that's the ugliest benzene I've ever seen. All right, and we will have kicked out our benzoate. What's up? What's it, right? Yeah. So you're going to end up kicking out one of your things. So you'll end up losing half of your molecule, which is again the criticism for using these. So half the molecule will go away, the other half will become a part of our new molecule, whatever that may be. So again, a little bit easier to use the chlorides. All right, speaking of chlorides, let's use one. Let's do some predict the products. I'm going to actually move this down just a little bit because it's in our way. Or actually, we have that pesky carboxylate in the way. Two things happening here, right? So the first step, I'm going to draw this as both steps because why not? Our first step here, remember, a Gilman reagent will make a ketone for us. So we're going to keep the carbonyl side of our acid chloride, and we're going to put on the Gilman reagent in place of where our chloride was. So in this case, it's methyl dimethyl lithium cuprate. We're going to put a methyl group on. That's step one. We make a ketone, a methyl ketone in this case. Step two is a reduction, right? We are going to reduce that ketone. And so we'll end up with a secondary alcohol. All right, so this is one way to end up with that if we wanted a secondary alcohol. If we tried to use a Grignard on this, methyl migber, if we tried the methyl Grignard, we would end up with a tertiary alcohol, right? But if we make the ketone and then reduce it, then we can have a secondary one. So we have many ways to go about this. All right, so our final product would be that secondary alcohol, and it's going to be, stereochemistry-wise, it will be racemic because the ketone is, of course, planar. Alrighty. Questions on that one? Do another one. That's that horrible thing there is an H, by the way. And that is ideally a six-membered ring, if I can draw properly. Let's take a look at what we have here. We have an acid chloride, and we have a secondary amine. We're allowed to react these, right? So what we're going to end up doing is replacing the chlorine with the amine, and that's all it is. They end up keeping the rest of the molecule the same. And we just stick on our amine. And we make HCl, right? And that HCl goes and reacts with the other equivalent of this the cyclopentylamine thing. So do we see how these transformations are taking place? And because we only have 2 equivalents, we're good there. If we tried a 3rd equivalent, thankfully, we're not going to get anything else to happen here, because thankfully we have a fully, happy carbonyl. But if we just put excess here, let's take a look at this. And I'm gonna mess it up. I'm gonna put a bromine this time. If we did this, just excess like crazy, first we're going to make this thing. Are we going to do anything else with this? Are we going to go like this? Are we going to make an enamine out of this? The answer is no, thankfully. We don't have to worry about this. Thankfully, this doesn't happen. I don't want you to just see carbonyls and be like, carbonyl plus amine equals enamine. Secondary amine, that is. This doesn't happen. Thankfully for us. Because the carbonyl of an amide is much less electrophilic. So it's not going to be strong enough to make an enamine. So we are safe there. So we don't even have to worry about it. So in the first one, we didn't have to worry because there was no hydrogens to worry about accidentally enamining. But even if you did have hydrogens you could make an enamine with, it's not going to happen because your carbonyl is not electrophilic enough. That you can't do a condensation with an amine. Alright, so we're stopping here, no matter how much amine we put in there. That's what we're going to end up with. We're going to end up with the amide. Alright, so only aldehydes and ketones will condense with amines. To make either your imine or enamine. Alright, so not going to happen with amides. Alright, so I'm just putting that out there so you don't just see, C double bond O. I must turn that into an enamine. Alright, so don't worry about that happening. Because it won't. Because it won't. Alright, so putting an acid halide with an amine will just get you the amide, no matter how much you put in. Alrighty. Any questions on any of these so far? Alright, so just to reiterate, anhydrides and acid chlorides all react the same way. So they do exactly the same reactions. You can make an aldehyde out of an anhydride or an acid chloride using the lithium tri-T-butoxy hydride. You can make, what else do we want? You can make a ketone using a Gilman reagent with an anhydride or an acid chloride. They act exactly the same way. All right, so those two are our most reactive and our most functionally useful. So they do exactly the same things. Let's look at esters. Esters are going to be our next reactive group. So acid halides are the most reactive, then anhydrides, and now esters. Esters are a third most reactive species here. There's going to be a ranking of 5, by the way. So these will be number 3 in the middle. So esters, we can hydrolyze them either in basic or acidic conditions. Let's look at basic first because it's easier. Here's an ester. If we are putting it in the presence of hydroxide, guess what's going to happen? Exactly the same thing. We've looked at. Except these are going to be much more equilibrium-like, because we're going to see that, well, we have two kind of equally good leaving groups now. Or equally bad would be a better way to say it. We're either going to produce an alkoxide or a hydroxide, both of which are good nucleophiles, right? They're not good leaving groups. But just by equilibrium, one of them is going to get kicked out. And so we can kind of make the choice that we're going to kick out our methoxy group. And we will make our carboxylic acid. All right, and then the methanol is just going to come and grab the proton off of that. Right, carboxylic acid much more acidic than methanol would be, so we're going to just finish off by making the carboxylate of it. We'll say Na. All right, so technically that's minus, this is plus. We make, in this case, sodium propionate, or propanoate, either way. Systematic versus common name. Common name is the first one, propionic acid, right? Propanoic acid, which sounds very much the same, is the IUPAC name. So you would end up making these out. Now this reaction, specifically base catalyzed hydrolysis of esters, is also known as saponification. For those of you who are multilingual, you probably understand some root word here. This is soap, right? In French, at least, I can go there. We have savon, right? Which is soap. So this is a soap-making reaction. And I think Armenian has a similar word. What's the Armenian word for soap? It is. Yeah, so there we go. So me, not an Armenian speaker, but living in Glendale for so many years, you learn things, right? So this is a soap-making reaction. These things are soaps. Typically, they're either going to be with a sodium or potassium, and they have longer carbon chains than these, but typically 18, 20 carbons is how long these chains tend to be for them to be good soaps, because if you have any idea how soaps work, they kind of form little micelles, kind of like phospholipids make their bilayers. Micelles are single-layered things, and they can trap fatty bits and have polar sides and non-polar sides and so forth. Interestingly enough, sodium soaps are the hard, like, bars of soap, and potassium ones are the soft soaps, so the liquid soaps. So, fun fact, there you go, your counter ion actually kind of matters this time. So it depends what kind of soap you want to make. So if you want to make a hard soap, a bar of soap, that's the sodium. And if you want to make a liquid soap, a soft soap, that's potassium. So you just use a different base, sodium hydroxide or potassium hydroxide. And fun fact, if in the lab, way back when, you spilled sodium hydroxide on your hands, you'll notice it feels very slippery and soapy. The reason for that is because your skin is being dissolved by the sodium hydroxide in much the same sort of reaction. So your cell membranes have esters, right? They have phosphoesters, and they're going to react the same way. And so your skin is being dissolved by the base, and that's why it feels so slimy and slippery. And hopefully none of you are foolish enough to have tried this, Eric. But that's the feeling you would feel on your hands with basic solution. Yeah, sodium hydroxide is our base here, right? Oh, well, either hydroxide will do it, yeah, for sure. So that's why we wear gloves and we wash our hands with strong bases and all that fun stuff. So that's the reason for that. Yeah. It's no fun indeed. So, yeah, so there's your fun fact for the day. So spill strong base on yourself, you'll clean yourself. Congratulations. By turning your skin into soap. So there we go. So that's the base catalyzed hydrolysis. So first step, nucleophilic attack, closes down, kicks out the group. And then because your methoxide is a much stronger base than your propionate is, it's going to go ahead and just deprotonate it. So just have that as in mind. Don't leave it just as the don't leave it as the acid form. If you want to make it into the acid form, you're going to have to do an acid wash. So let's just kind of condense all this information. Ester plus sodium hydroxide. We'll use KOH this time. You make your carboxylate and your alcohol. And then if you do an acid wash, you will get your carboxylic acid out. All right, you can't just use water, you've got to actually use an acid wash this time. Because the carboxylate is pretty stable, so you need something a little bit stronger to protonate it back to the carboxylic acid. So remember, this is technically a salt, so these would be ionic compounds, so you will see them generally more solid, but just depends how long your carbon chain is. Cool. Okay, so that is the base catalyzed one. We're going to see the acid catalyzed one. We should put a little bit of heat with this too. We're going to end up getting the carboxylic acid out and the alcohol. Both of them. And this is the opposite of the Fischer esterification. I think it's with the C, yeah. So to make the ester, remember we took an acid and an alcohol and heated them up with acid and we got out our ester. It goes exactly the opposite way too. Let's take a look at the mechanism. It's entirely the opposite of what you saw for making the ester via Fischer esterification. So we'll take a look here. All right, so first step in an acid catalyzed process. And this time, yes, we are starting from the carbonyl. I'm 100% sure of that. With an acid catalyzed process, we have to do that. And we'll look at these, we'll compare them side by side once we're done with this mechanism. So we will have protonated our ester, specifically the carbonyl carbon, making it more electrophilic, such that now we can have a fairly weak nucleophile like water come in. And by the way, all of these will be equilibrium reactions, right? So I hope I don't forget that these are all completely equilibrium. So we saw that to get the ester, we can make it go that way by taking out the water. It's completely equilibrium, so it goes back and forth. So we will have now our intermediate here. Technically, if I want to do this in 3 steps, here comes another water. It's going to come in. So now we have, and I'm going to just draw them both up here if that's okay with everyone. So again, equilibrium. Now we're going to protonate one of these, and because we want to get rid of the alcohol, we're going to protonate that side. So here's our acid again. Protonate the alcohol bit. Right. And again, if you just want to do a proton shift, I'm okay with that. I don't need you to show me, oh, water comes in, grabs the proton, and then this guy comes and grabs it right back. I'm okay with just doing a proton shift. Cool. So next, we're going to go ahead and condense down. Kicking out our alcohol. Can I do this in one? I can fit it here. We lose our alcohol, which, by the way, should have had the prime this whole time. There we go. And then now our water comes in and grabs the proton away, giving us our acid. Done. All right, going vertical for a second here so we can see it all. So, first step, protonation. Remember, in acid-catalyzed processes, that's always the first step. So we're going to go ahead and protonate our carbonyl oxygen. Gets attack from a water molecule. We have some proton shifts happening to end up putting the proton onto our alcohol. We condense down, taking out the alcohol, and then we will deprotonate as our last step. And remember, for Fischer esterification, it's all the same as this in reverse. So if you want to start at your acid and go to the ester, you would just use your ROH as your nucleophile instead of water. And so it's exactly the same process. All right, so one more thing to notice here, if we're going to be a bit more nitpicky about mechanisms, notice that nowhere in this mechanism do we have an O-. We have no negative charges anywhere in this mechanism. And that's the ideal situation for an acid-catalyzed process. Because if you do have negative charges, they would have immediately reacted with an acid, right? Because negative charges tend to be bases, right? So it's important that if we are showing the mechanism for an acid-catalyzed process, that we don't have any strong bases present in our mechanism, because they just wouldn't happen, right? We're only going to see mild bases present in an acid-catalyzed process. Mild like water. Water is a mild base, right? It's not a strong base at all. But O- is a strong base, whether that's hydroxide, whether that's an alkoxide, whatever it may be. So just keep that in mind. So note here, are present in the acid catalyzed mechanism. So we can't just attack the carbonyl directly. If we do this, we end up with this guy. It would just close down right away. It's a strong base, right? So this is not something that's going to happen. Not going to happen here. All right, so we're not going to end up having this. We're going to end up only having protonated species throughout the mechanism for this reaction. And we see in the base catalyzed, we have only negative charges. We have no positive charges. Okay, the sodium's positive, whatever, who cares? We have no negative charges on, or sorry, we have no positive charges on oxygens or anything else in our base catalyzed mechanism. We have a negative OH, we have a negative carbonyl, we have a negative methoxide, and we have a negative carboxylate. So we have negatives everywhere. No organic positives. Yes, we have a sodium positive. That's not what we're focusing on here. So base ones, we don't have any strong acids. A protonated alcohol or a protonated ketone, those are strong acids. So we don't have any of those present in our base mechanism. Just like with the acid mechanism, we don't have any strong bases present, only positive charges here. All right, and in base, only negative charges. All right, so that's just a rule of thumb. Good practice for mechanisms is to be consistent with your conditions. So basic conditions, keep everything negative. Acidic conditions, keep everything positive. All right, I will write that down. All right, so just we'll use purple. So note acidic conditions want to have minimized number of negative charges. And so we saw that with the, here we had 0. Okay, yeah, we have the H, actually, yeah, no, not even a single one. This is positive here. We have all these positives, no negatives. So acidic conditions, you minimize the number of negatives, keep things positive. For basic conditions, you minimize plus charges. Keep things negative. So just be consistent with your mechanisms. So that's a hint. If I'm seeing all these negatives in your acidic condition mechanism, I'll be very sad. So don't do that. All right, so that's just a note on keeping things consistent. Let's see, what else can we do with an ester? We can reduce them. So we can hydrolyze esters. So we can take them to turn them into acids. So that was hydrolysis, saponification, and then the acid version of it. We can also use reducing agents. Important thing here. You will do the same thing as before. You will end up needing excess or 2+ equivalents. And you will go all the way. Your milder ones, typically not so much. So that's beneficial for us. So we can use these reducing agents, milder reducing agents. And generally speaking, the NaBH4 will react with something more reactive over the choice of the ester. So if you had an aldehyde or something, or a ketone, it's going to react with that instead. And it's slow enough that you can just use one reagent, one equivalent, and it's not going to go ahead and react. But if you put lithium aluminum hydride, that's strong enough, it's just going to see any carbonyl it can, it's going to start reducing. So with sodium borohydride, you're a bit safer, as is your bet. Okay, but with the lithium aluminum hydride, you're going to do the same thing you did with an acid chloride. You're going to reduce it all the way down. All right, and then you do the acid wash, or water wash at the end. All right. With Grignards, esters behave the same way as with the acid chloride. So we end up doing exactly the same thing. We make our, you would need 2+ equivalents of this, and again, water wash at the end. You're going to get the same thing, your tertiary alcohol out. So hopefully we're seeing it's much the same things, right? Take any of these so far, put it with a Grignard reagent, you make a tertiary alcohol. You put on 2 equivalents of your Grignard. Pretty much the same thing, right? We put water with it and acid. With any of those 3 that we've looked at so far, acid chloride, anhydride, or ester, we get the carboxylic acid. If we put lithium aluminum hydride, we get the primary alcohol. So all the same things. So thankfully for us, they're very similar. All right. However, that's it. We typically do not react these with amines, sorry. With amines, you typically will not get a reaction to happen here. So we don't have to worry about it. So no reaction happens with amines. That's the only difference, right? So we can do all our crazy stuff. If we wanted the aldehyde, we would use the lithium tri-T-butoxyhydride. Same exact things as before. The only thing that doesn't work will be the amines. Acid chlorides, that's what I'm trying to say. So we are going to really only get those to react with acid chlorides or anhydrides, so they're not going to react with esters. All right, so that's esters. Last one we have, second to last one. Carboxylic acids, what do they do? What do these things do? What can we do with the carboxylic acid? Well, we can react it with a base. Okay, we've made a carboxylate. So we can do acid-base reactions. Very exciting. We can do thionyl chloride, gets us to the acid chloride. We can heat the crap out of it to get an anhydride. We can use an alcohol to get an ester out. That's pretty much it. That is pretty much it. So I put 3 deltas, by the way, because that's a crap ton of heat that's needed to anhydridize them. That's the new word for the day, anhydridize. I guess the word is dehydrate, but anhydridize works. So these ones are pretty boring. Pretty boring. If you try and react these with Grignards, not going to happen, right? Because you have acidic protons in the presence of Grignards. Grignard is just going to eat it up. If you try that, just have a carboxylate again. And you will have made, yeah, go ahead. That's esterification, right? That's the Fischer esterification. So we looked at the reverse of that. That's the going forward one. Dehydration. No. What would we call this? Halogenation? If we wanted to. This one is just a very sad. You've just messed up your Grignard reagent. So all that work to make it, and all for nothing. So not really going to work there. All right, so you would need, if you wanted to do a Grignard on this, you would need to activate it. You would either need to turn it into an ester, an anhydride, or an acid chloride. So you can't just go ahead and use the acid as is. All right, you would need to activate it first. So let's look at the reactivity of these. In terms of reactivity, of the 5 major ones, we are going to talk about nitriles tomorrow, but we'll look at that a little bit later. Oh wait, did I talk about making? Oh, I forgot one on esters. Okay. Let's hide this away. Actually, I'm going to move this one down. I lied. We're going to keep it with this. With the esters, we have special lithium aluminum reagents for this. We use the diba. Will give us the aldehyde. Diba is di-isobutyl aluminum hydride. So there's no lithium here, just di-isobutyl aluminum hydride. This reagent will get you from an ester to an aldehyde. And we'll see it will also work on a nitrile. So we're going to see that tomorrow when we talk, not tomorrow, Wednesday when we talk about nitriles, that will have this reagent there as well. So add this to your toolkit. It works nicely with esters. All right, and it's really essentially the same thing, just a bulky aluminum hydride. All right, what was I going to say? So reactivity. So we have acid halide is better than anhydride, is better than ester, is better than acid, and all of these are going to be, because I have no room, these are all going to be much more reactive than amides are. So acid halides are our most reactive, anhydrides second most, then esters, then acids, and then finally amides. We're going to see amides are the least reactive, and we're going to see why starting on Wednesday. All right, and nitriles are just kind of doing their own thing, so they act very differently than the rest of these. All of these are carbonyl based, right? So acid halides, typically that's chlorine, right? We don't see the bromine as much. Anhydrides, esters, acids, and then finally amides. I'm going to put them up here. So amides are our least reactive of all of these. And so we're going to take a look at that next time. All right, so that's it for today. So we'll talk about amides as well as nitriles, and then maybe we'll start enolates as well on Wednesday. Okay? Cool.